After today, there's just the final. And the final's on Thursday. We've talked about it before. It'll be here in the classroom. 2 hours is available, and so that means there will be more problems than you've had on the midterm exams. I'll provide an equation sheet, the same one that you had on exam 2. So any questions about the final, the format of the final exam? All right. Well, today we're going to be talking about dimensional analysis and similitude. That's chapter 8 in the book. And it's kind of an interesting topic, and it's something we could spend easily the entire semester discussing if we had the time. Many of you may go on to graduate school, and it's something that if you end up doing physical experimentation, understanding dimensional analysis is very useful to help you identify which parameters you should measure when you're performing experiments. We'll begin by talking about the idea of dimensionally homogeneous equations. And Isaac, do you have a question? No? A dimensionally homogeneous equation is one that has consistent units on both sides of the equation. And so an example of that here is an equation that relates the quantity of flow for a weir. And so a weir is just an obstruction on a channel where water is flowing over the top of an obstruction. We'll look at weirs next semester when we get into hydraulic engineering, but the flow over a weir is dependent on, first of all, 2/3 times c, where c is some energy reduction factor. It's just sort of like a factor that's unitless and related to how much energy is lost as water approaches the obstruction and flows over the edge. But length does have units. Length would be units of meters or feet, depending on what unit system we're putting in. And they're really only, when you break it down into the most fundamental terms, there's only 3 units out there. There's length, mass, and time. And every other unit is some rearrangement of those 3 base building blocks, length, mass, and time. And so here we abbreviate. Anytime we want to look at whether a formula is dimensionally homogeneous, we'll look at, on the left-hand side, we know flow rate would be, for instance, cubic meters per second, and so that's length cubed per time. And then on the right side, we're interested to know, is that the same? And so the length of the weir, how wide the obstruction is in the flow, would have units of meters, which is length. Underneath the square root here, g is, of course, 9.81 meters per second squared, and so the meters is units of length, time from the seconds is t squared, and then length to the 3 halves, and so that's 1.5, and so we have 1.5 plus another half plus another 1 gets us to 3 for the length, and then since t was squared but is in the square root, then it ends up just being units of time. So this is dimensionally homogeneous. And it's an indication that you're using a formula that's derived from the first principles of physics, rather than just based on observation and an empirical curve-fitting expression. Now, dimensional analysis is a way to recreate what's happening in the world with a smaller sized model. And the model is sometimes a physical model and sometimes it's a numerical model. But dimensional analysis will allow us to find out how the behavior of a small scale model can be applied to a larger size prototype. And why we have to be aware of that is because things that are small sometimes are unusually strong, for instance. So just take as an example, maybe many of you had small toys like a Matchbox car when you were small, when you were younger. And so, you know, that's a scale replica of a full-size prototype car, but if you drop it from chest height, think about the equivalent, a full-size car being dropped from an equivalent scaled height, the sort of damage that that would do to a full-size car, and yet you drop the model and it doesn't seem to be affected in the same way. It's not really the same like explosion of broken parts that it would be otherwise. And so it's not really a Matchbox car, just as an example, isn't a very good model if you're trying to simulate the forces and the reaction to forces that can arise in a prototype. So if we look at another example, the idea of wind tunnels and what's happening inside of a wind tunnel on a model that's simulating a full-size airplane. We may want to know how big the model airplane should be to realistically simulate what's happening in the wind tunnel. And so, a small-scale model can just be decorative, but can also be really useful in making subtle changes to the shape of an aircraft wing, or trying out you may have seen on a lot of planes nowadays have winglets on the end of the wings to try and reduce fuel consumption. And those were developed in wind tunnels and with numerical experiments, computer simulations, and they knew what would happen before they bolted them on the end of actual wings. And so dimensional analysis helps a lot. And it does that in civil engineering as well. And one of the most well-known examples of a physical model in civil engineering, the Army Corps of Engineers in San Francisco has a model of the San Francisco Bay that was active until relatively recently. It was developed long ago, and just to understand the complex ecology and the complex hydraulics of several rivers going into the bay and the watershed, they built this enormous physical scale that's about the size of a football field. It's all indoors. And there is a video that just gives a brief overview of that physical model, and we'll take a look at that just so you can understand it better.
We're here in the San Francisco Bay Model Visitor Center, where you have a chance to see the only operational hydraulic working model in the United States today. The primary purpose in building the model was to test the John Reber plan. John Reber wanted to dam the bay. He wanted to build 2 freshwater reservoirs by constructing 2 large dams, one where the Bay Bridge is and one where the San Rafael-Richmond Bridge is. After the construction of the Bay model from 54 to 57 and all the tests of his theory and his idea, it was summarily rejected. Fortunate for all of us, or we probably wouldn't have a San Francisco Bay today. After the construction of the model, it was used as a scientific operational research test facility from 1954 until January of 2000. Scientists could predict impacts on oil spills, major storms, but mostly the impact of man-made projects on any part of the shoreline. The San Francisco Bay model represents about 1,600 square miles of land and water resources, about 70 miles inland from the coast of California. The Pacific Ocean is built all on sand, but the entire rest of the model and the delta are built out of concrete slabs. There's about 286 of them. They're 12-foot squares. They weigh about 7 tons each, and they're all elevated about 30 to 38 inches up off of the floor. We have 2 supercomputers and also a lot of very sophisticated technology in a little facility called the Tide Hut. Every morning when we turn on the computer, it takes about 20 to 21 minutes to flood the entire model and the delta with about 135,000 gallons of water. At the end of the day at 4 o'clock when we close to the public, we close the system down, all the water drains back into the sump tank. You'll see throughout the model there's about 250,000 copper tabs. They're embedded in the concrete, and their primary purpose is to help provide frictional resistance to help create the right tides and currents. There's 3 specific criteria that are important in analyzing how the model is calibrated and how it operates. The horizontal scale of the model is 1,000 to 1. So for every 1,000 feet underneath the Golden Gate Bridge, 1 foot in the model. The vertical scale is 100 to 1. So for every 100 feet underneath the Golden Gate Bridge, 1 foot down in the model. But the most important factor is time. Now a lunar day is like 24 hours, 54 minutes, so many seconds. But in the Bay model, that happens every 14.9 minutes. So every 14.9 minutes in the Bay model, you have 2 high tides and 2 low tides. Mathematically, it's changing about every 3.78 minutes. The area of the Bay model, what we call the San Francisco Bay Model Delta area, This represents about 1,600 square miles. It's about the size of the state of Rhode Island. When you're standing on our observation deck looking down at the bay model, it's about the same as flying in an aircraft above the city of San Francisco at an altitude of about 10 to 12,000 feet looking down at the bay.
All right. So that gives you an idea of it's still operational, but it's not used for calculations in the same way that it used to be. It's been replaced by just strictly computer models at this point. One of the main principles that's employed in constructing a physical model is the idea of similitude. And geometric similitude is what people are generally familiar with in the relationship between models and prototypes. And geometric similitude is just the idea that you should have a scaling of the dimensions, so that if you have, for instance, a 1 foot long boat as a model and it's 100 to 1 scale, then that means the prototype you're trying to model would be 100 feet in length. So every parameter from the model to the prototype follows the same geometric ratio. But more interesting to us than geometric similitude is dynamic similitude. And dynamic similitude is what you have to use when you want the forces for the prototype to scale down to the size of the model, so that you can actually simulate the amount of scour that would occur in a real-world spillway, like this is illustrating. This is basically looking like a dam, and the water flowing over the face of a dam is called a spillway, and it's a kind of a dangerous situation because the water gets so much velocity as it's falling downward over the face of the dam that the flow can become what's called supercritical, and then when it reaches downstream at the end of the spillway, it has to jump back up to a subcritical depth. And so there's a lot of turbulence and a lot of energy gets exerted here in a hydraulic jump. And so whenever a new dam is being designed or an old dam is being retrofitted and refurbished, they do a lot of simulations to try and understand what will happen, where the hydraulic jump is going to set up, how much energy is going to be exerted by the hydraulic jump. And so to do all that, the dynamic similitude is a way of making sure that the forces on the model correspond to what will be experienced by the prototype. And the way that you achieve it is to ensuring a correlation between the Reynolds number of the model and the prototype. Reynolds number, of course, is a dimensionless parameter that we've used in the past to indicate whether the flow is laminar or turbulent, and how far beyond the laminar range if it's in turbulent flow. We're going to do some calculations related to dynamic similitude here in just a minute. One of the other advantages that we have when we're doing model simulations is that it gives us the flexibility to use different fluids besides just air. Even if what we're trying to do is understand, for example, the flow of air over a wing, we could switch to water as a fluid instead of air if that meant that we had different velocities that are more favorable for the pumps we're trying to use. Or vice versa. If you're trying to understand the scour on a submarine, submarines can experience cavitation on the propellers that they have on the end. And cavitation, remember, is a very localized low pressure that causes bubbling, and the collapse of those bubbles can cause damage, but it's also very noisy. And so there's a lot of research that's done on trying to make submarines more quiet so they can be more stealthy. And so model scaling can be used in a situation like that, where if you don't want to use a billion-dollar submarine for this research, you can't take it out of commission, but you can use small-scale models and change from one fluid to another. So you could use a more viscous fluid like oil in place of water, and it may give you advantages in terms of the speeds that have to be used for the scaling. So here's an illustration of that. If we are trying to simulate the performance of a full-scale prototype blimp, and we're doing it with a model that is going to be 1/10 the size of the prototype. So the prototype itself is 60 meters long and 5 meters wide. The geometric scaling of it is pretty easy. That means that the The model we're going to use will be 6 meters instead of 60, and instead of 5 meters wide, the model would just be 0.5 meters wide. But we have to look at the velocity that we expect the prototype to fly at 10 meters per second. And so the question here is, what wind speed should we use in the tunnel? The way that we accomplish this is by setting the Reynolds number of the model equal to the Reynolds number of the prototype. And let me just open this file. All right. Reynolds number, of course, can be calculated by the velocity, the length, density, and viscosity. Now, when we're talking about flow through a pipe, the length parameter has been diameter. But here, we're talking about blimps, not pipes. And so in place of diameter, we'll use the physical length of the blimp. And so what we want to do is we want to relate the velocity that the model is going to experience, the velocity of air that's going to be going over the model, with some length parameter describing the model, the density of the fluid that the model is going to encounter, and the viscosity of the fluid that the model is going to encounter. And then we'll set all of those things equal to the same parameters but for the prototype. All right, so we want to ensure that the Reynolds number experienced by both the model and the prototype is equal. And that tells us, for example, we know the prototype's going to fly at 10 meters per second. So the question is, what wind velocity should be used in the wind tunnel for the model? Okay, so I'm going to rearrange this for the solving for the unknown. We've got the velocity of the air in the wind tunnel that the model will experience. If we rearrange that, then that is V sub p, L sub p, the density of the prototype, and the viscosity of the model, divided by the viscosity of the prototype, the length of the model, and the density of the model. So just rearranging for the unknown, where it says there in blue, the wind speed that should be used in the wind tunnel. Now, the wind tunnel and the model are both going to be encountering air. And so the viscosities are the same. We can cancel that term out. The viscosity of air is going to be the same whether it's the wind tunnel or up in the atmosphere where the blimp itself is flying around. And since it's air, that means we can also cancel out the common density of the fluid. But the length parameters are different. And that means that the wind the model is going to experience needs to be different as well. So the velocity of the prototype, it's going to fly at 10 meters per second. And if we substitute in the length parameter of the prototype, that means it's 60 meters. Or we could have put in 5, or we could have put in 10, and then just use the corresponding smaller dimension for the model. So the length of 60 meters, the model has a corresponding length of 6 meters because it's a 10-to-1 model. And what that tells us is that actually the velocity of the air in the wind tunnel for the model, it should be 100 meters per second. So if we put 100 meters per second on that smaller scale model, then it's going to behave like the bigger one would when flying at 10 meters per second. So think again back to that example of the Matchbox car and how, you know, it just doesn't seem to match up because it's so much smaller, it has an unusually high strength. And so here the model, we have to have the wind really blowing on it quite hard because it's smaller in order to get the forces to scale in the same way that they would for the prototype. Do you have a question? All right, we set the Reynolds numbers equal to each other. So here we have the Reynolds number of the model is equal to the Reynolds number of the prototype. And so that's where these come from. And I'm rearranging to solve for the velocity of the model. So that means that the L has to go down here for that one, and then it was already there on the other side. Okay. Are there other questions? All right. Oops. All right. So why don't you try this one? Here's a question related to flow through a pipe. Again, you need to set the Reynolds numbers equal to each other. The Reynolds number for the prototype should equal the Reynolds number for the model. So here we are going to, in the full-scale example, we're going to have oil flowing through a 15-centimeter diameter pipe. The full-scale situation is going to have a flow of 2 meters per second. Now, if we want to model that in the lab with a smaller pipe, if we want to model that with a 5-centimeter pipe and we want to use water instead of oil, then what velocity should we use in the lab when we do that with water instead of oil? So you can use the Reynolds number as that we had on the board from the previous example, or here is the Reynolds number that's using the kinematic viscosity. And of course, the kinematic viscosity of water at 20 degrees is just 1 times 10 to the minus 6 meters squared per second. All right, so see if you can calculate what velocity should be used in the 5-centimeter pipe so that we have an equal simulation. All right, so if we list all the parameters for the model and for the prototype, looks like I switched the terminology. It ends up not mattering which one you call the prototype and which one you call the model. I guess ordinarily you'd think that the prototype is going to be the larger of the two, but it's possible that you could use something very big to simulate what's going to happen with something small as well. So here we have all of the parameters for each one, set the two Reynolds number equal to each other, and it tells us that the flow with the water in the pipe, the smaller 5-centimeter pipe, should have a velocity of 1.5 meters per second in order to get similitude. Yes?
So you don't have to convert the diameter into meters because it's a lot of
Exactly right. Ever, yeah, because it's going to cancel out the units as you mentioned. So you could mix BG units with SI and everything would be fine. Yep. Good question. All right. Other questions? Where things get really interesting is where you're doing experiments to try and figure out what equation should you use to solve a problem. Let's say that you've got water flowing through a pipe and there is an opening in the pipe. If you're thinking in 3 dimensions, what this would represent is this would represent an orifice inside of a pipe, but you've got flow going the opposite direction through that orifice inside the pipe. So, how is this going to behave? A situation like this. So you'd have to do experiments, but you can get an idea of what the result may look like through dimensional analysis and developing something that are known as pi groups. You can do numerical solutions where you have a computer simulating it, and you have to really have pretty sophisticated computers with a powerful processor to be able to do it at the resolution that you'd need to get a high amount of accuracy. So the physical testing can be more accurate to predict what will happen in a real-world environment, is building a model to simulate it. So we have these smaller scale models because full-size testing isn't practical, but you have to know how to relate the full scale to the smaller scale. So the method we're going to go through now is used a lot for people who are designing experiments to try and understand if you know parameters that are related to an observed effect. For example, a sphere that falls through a fluid. If you want to know what the drag force is going to be on a sphere, and you want to be able to predict the drag force, then you may be interested to figure out which parameters you'd have to study and how they would be combined with the ultimate equation that you're trying to develop. Reynolds number is one that's really important both for the similitude that we were just talking about, but also in dimensional analysis. So we know that Reynolds number is a dimensionless quantity. It's an example of something that's known as a pi group, because if you look at the units of all of the things that go into Reynolds number, they cancel each other out, and Reynolds number itself is unitless. And so remember how I said earlier today that everything boils down to 3 types of units? Well, it's already in those base units when we talk about density. It's mass per length cubed, and velocity is length per time. But even things like viscosity of a fluid, where it starts out as Newton seconds per meter squared, you can break the newtons up into a kilogram meter per second squared, and then you see that all that's left when you cancel out the common terms are mass, length, and time. So what we're going to be doing today is looking at different ways of breaking down the units of complicated parameters into the 3 base combinations, and then rearranging groups of parameters until the group itself is unitless. And so Reynolds number is unitless because all of the parameters that go into it, when you combine the units together, it divides to 1. And one way of expressing that something has no units is just to, in brackets, have the number 0. That's a kind of a common notation for saying that it has no units. All right, so the Buckingham pi theorem is that you can create a certain number of dimensionless units based on how many variables come into play for a formula, and then the number of dimensions that are in those variables. Let me give you an example, because this is just already so abstract that talking about the theory of Buckingham pi theorem without the illustration is probably not time well spent. So let's say we've got marbles that are falling downward through a fluid. They don't instantly go at the same speed that they would if they were falling downward through a vacuum, because the water has to deform out of the way of the spheres as they fall downward. Just maybe from observation or experience or a little bit of preliminary testing, you could find out that how much drag force there is as the sphere falls downward is a function of how fast it's falling, the density of the fluid, the viscosity of the fluid, and then the diameter of the spheres. So we know that those things are all somehow related, but we don't know exactly how they're related. And we say, for instance, we don't know what the formula should be for what is the drag force as a function of those other parameters. The Buckingham pi theorem and the process of assembling dimensionless groups allows us to develop a new equation. So we can find out what is the formula for drag force just by knowing that these have been observed to affect it. All right, so here there's 5 variables. There's the force of drag, velocity, density, viscosity, and the diameter. And among those 5 variables, there are all 3 of the dimensions: length, mass, and time. The velocity, for example, is length per time. We've already looked and seen that the density is going to have the kilogram parameter in it, and so then that's all 3. So what that means is that if you have 5 variables and 3 of the dimensions among those 5 variables, then there should be 2 pi groups. So n is the number of variables, m is the dimensions that there are, and so 5 minus 3 means that there will be 2 groups when we rearrange all these parameters according to the procedure I'm going to show you here in a moment. So the process we'll follow is we've already identified the variables that are significant. We're going to put a table together that lists the variables and the dimensions that correspond to them, and then we'll go through a process of combining groups together until all that's left are combinations of the variables that have no dimensions, so dimensionless groups. Sorry about that. It seems that spammers have gotten my phone number. All right. So here's what we're going to do. I'm going to put a table on the screen, well, on the whiteboard here, that has those dimensionless groups that we're working towards. And so the variables, now there will be a Chapter 8 question on the final. I realize that you haven't done a homework assignment on Chapter 8, and that's why I'm going to give you an activity today to work on here in class. It's to kind of get a little bit of practical experience with Chapter 8, but I'll have modest expectations for how familiar you are with this content. So know it, but don't stress over it, all right? So don't ignore this stuff just because there's no homework assignment. So our first variable is the force of drag. The next variable is the velocity that it's falling through the fluid. Then there is the density, there is the viscosity, and the diameter. So those are the 5 variables that we're going to be working with. And then the units for each of them is what we're going to first look at. And so drag force, over here, let's assemble our look at each of the variables and what units they've got. Okay. All right, so force has units of newtons. All right, and newtons, if we break it down further, it's a kilogram meter per second squared. So that means the units of force are mass times length divided by time squared. Velocity is meters per second, which is just length per time. If we want to look at the parameter of density, okay, the units of density, kilogram per cubic meter, so that means we're going to call it mass per length cubed. Viscosity has units of newtons seconds per meter squared. And so that is kilogram meter per second squared for the newtons. And then there's the other second and the meter squared that was there before. So that cancels out to kilograms per second meters. So that is just mass divided by time times length. And finally, diameter is just meters. So these are the dimensions I'm going to put in the table over here, just the combinations of M, L, and T. Okay, so force, when we did that work over on the other panel, it was mass, length divided by time squared. Velocity was length per time. Density was mass divided by length cubed. Viscosity was mass divided by length times time. And diameter was length. Okay. Draw these lines here so we try and keep things at least a little bit organized. All right, so this is our first step. We've got just the starting point of, we know there are 5 variables that are somehow related. The drag force is a function of these 4 other parameters. I'm just going to call this step 1 is the beginning. Now, here in the next phase, I'm going to try and take out one of the dimensions in these units here. And I'm going to try and simplify the units of length. Any place I see length, I'm going to try and cancel it out by combining d. So for example, look at velocity. I could cancel out the length parameter by combining velocity and d in this way. If I say velocity divided by d, then I'm going to have length per time divided by length. And all that'll be left is just units of 1 over t. So I've got my variables and my units. So what I did, I used d as kind of like a tool to cancel out the units of length here in velocity. And I can do the same thing in the force term. If I divide by d, it's going to cancel out that length parameter. So force divided by d, and what I'm left with is mass per time squared. So I'm trying to simplify the units. And as I do that, as I'm simplifying the units, I'm creating these groupings of variables. All right, I can cancel out the length parameter here on the density term. And what I'm going to do for that is I have density, and if I multiply it by diameter cubed, then that'll cancel out the length to the 3rd power, and all I'm left with is units of mass in that grouping. And then also I want to have viscosity multiplied by diameter, and then I'll just have units of mass per time. And once I have started using one of these variables in combinations with other groups, then I cancel it out of the table. I'm not using it again. So the d exists in these remaining groups, but it's not continuing on its own. And the units of these groups are simpler than they were before. Remember, our overarching objective is to try and create combinations of variables that don't have any units. I mean, we could have done this just like with lots of permutations, you know, like just a random assembling of these 5 variables until we checked the units of every resulting group and found out how many of them were unitless, but this is a little bit more of a guided approach. So this is our second phase. In phase 3, we're going to do the same thing. We're going to have groups of variables. We're going to look at their resulting units and try to reduce the number of variable groups that we have by combining them together and simplify the units groupings. Yeah, I used d because we had length by itself, and it just seemed like a simple starting point. But it's not like there's just one right answer. There can be multiple paths to achieving the same end result in these combinations. But that is why I chose this first one, is just because L was there by itself. So you're right that maybe my next tool will be to, here I've got the density times diameter cubed with units of mass. I'm going to use this as a tool to try and cancel out mass in other places. So if I do, for example, force, density, diameter to the fourth, then that's just going to have units of 1 divided by t squared. Because before it was mass divided by t squared, and then here I can cancel out the mass by dividing this whole expression by density times diameter to the third. So it'll be diameter to the fourth, since there was already 1 diameter there. And then here's the density. All right, so I can do nothing to simplify the velocity divided by diameter. It already didn't have mass in it, so it sort of carries through unchanged in this phase. I'm not going to be using this group anymore. It's sort of out of the equation. And then there is a mass here that I can cancel out. What I will have is viscosity density diameter squared, and it'll have 1 divided by t. And so it is this expression divided by the one above it. And so what's left is just density squared. All right. So now all we've got left are these groups that have units of time. And we can combine them together in our last phase. We'll have some variable groups, and we're going to take a look at the units of those variable groups. All right. What I'm going to do is I'm going to use velocity divided by diameter to try and cancel out the t in other spots. So for example, if I combine velocity divided by diameter with this bottom term here, I'm going to have to actually multiply this term by d divided by v. So if I have viscosity, density, velocity, diameter, then that is unitless. Because what I did was I invert that so that it is t in the numerator instead of in the denominator, and multiply it by the expression. Or you could just, this one divided by that one will also give you unitless. And after canceling out the common d's, all that's left is this one. So this is a unitless expression. And I can use, I have to use the same one, because it's going to be canceled out when I'm done with it. I'm going to use the same one in combination with the top group. And what I end up with is force divided by density, velocity squared, diameter squared. And that is also unitless in the end. Now, the 5 minus 3 thing that we did at the beginning to tell us how many groups we expect to see at the end, that told us there should be 2 groups. And we found both of them. So, just trying to randomly assemble these 5 variables by multiplying and dividing, that would have, it would have been a pretty exhaustive procedure. But this, although it takes some getting used to, it's pretty weird and confusing the first time you see it. You'll pick up how to do it once I give you the chance to start working through it yourself. Now, the interesting thing is what this says is that we can set these two equal to each other. So what if we say the force, density, velocity squared, diameter squared is equal to viscosity, density, velocity times diameter. All right. So remember, all we wanted to know in the very beginning is what's the formula for drag force of a sphere? We can use these to tell us what is the formula. So I'm going to solve for F. I've set these two pi groups equal to each other, and if I solve for F, what I'm left with is that F is density, velocity squared, diameter squared times the viscosity divided by density, velocity, diameter. So though cancels out the density, the velocity and the diameter both go down to that. And so it's just left with velocity, diameter, and viscosity. And if you look up the Stokes law is the actual formula that's already been long discovered in the past. Stokes' law says that the drag force of a spherical particle is actually 3 pi times the viscosity, the diameter of the particle, and the settling velocity. And so we can't know in advance what's the constant, because a constant is itself unitless. But we did correctly, by assembling the pi groups and setting them equal to each other, figure out that the drag force is a function of the viscosity, the diameter, and the velocity. So I'd like you to get some experience assembling these pi groups and doing a similar analysis. So I've got an in-class exercise to give you. Are there any questions related to the table and which steps, how things canceled out? The handout that I have for you, I've actually, if you can't figure out what to do for the steps, I've given you hints at the bottom of the page. It tells you what to do in the first step, what to do in the second, and so on. People never get excited about pi groups. Sometimes people get excited about cavitation, but I've yet to meet a student who gets excited about pi groups. Do you guys need one more? You're excited? Well, then now I'm excited. It's kind of a puzzle in a way. You think of it like Sudoku. Maybe it'll be enjoyable just for that abstract reason. This first part's just to get you thinking in terms of units. All right. So you can do it in different orders. I had some suggested steps here in case you got like hung up or confused on what to do next. But there can be like a different order in assembling them, and so your solution may end up looking a little bit different. And then the other thing I can mention is that there could also be the inverse of these. And so here you'll notice that there's two possibilities. One is big D divided by little d. Well, you could also do little d divided by d, and it's still unitless, right? And so the thing I did in the first step was I canceled out diameter. I used diameter to cancel out length. And so this is going to be the tool that I use to simplify the units of other expressions. And so everywhere there was a length term, I'm going to divide or multiply by d to get it canceled out. So here, that meant dividing by d, and that's unitless. There was nothing in time. But here, for density, it was mass divided by length cubed, and so I multiplied by d cubed. And then that canceled out the length that used to be in the denominator there, and it just left the mass only. So big D divided by little d, that means I'm going to have here as my second dimensionless pi group. The first was this one. Here for the unit weight, here were the original units of unit weight, and I want to cancel out the L term, so I'm going to have to multiply by d squared to get that. And so you can see the units that are left over when you have these two things combined doesn't have any length parameter anymore, but it still does have mass and time. So you go through this whole process and you end up with 1, 2, 3, 4 pi groups. And so that's the process to go through. On the exam, won't ask you to make one of these tables, but I may ask a short answer conceptual question, which we haven't had before on the exams just because of a lack of time, but on the final exam I may choose to give you 1 or 2 conceptual questions. And so, are there any questions about this example? All right. Well, to conclude, let's look at the announcement slide one last time. The final exam is on Thursday here in this room starting at 10:15. I'll print out the equation sheet, so you don't need to bring anything except for your calculator, pencil, and well-rested brain. No overnighters, right? No cramming on Wednesday night. All right. See you then.